So here we are continuing with the May 15th class as part 2. And you remember we had a few questions we were trying to answer. The first question was, why are salt solutions sometimes acidic or basic? And I just finished a video on that. Now we're going to take a look at some problems involving the pH of salt solutions. So if I have a solution, say, of sodium acetate, or we'll use potassium acetate because I was using that a minute ago. All right, I put that in solution. It's going to come apart like this, like that. All right, and these are going to be aqueous, and this is going to be aqueous. Now we were talking about the ions from weak bases will react with water, or the ion from a weak acid will react with water. This is an ion from a weak acid. So I always like to say that the ion from the weak thing, or from weak things, hydrolyze. They react with water. So the ion from the weak thing hydrolyzes. All right, so in this case, it's the ion from the acetate that reacts with water. So I'm going to have C2H3O2. It's going to react with water. It's going to create, and then the OH is going to be left behind. Now, if we knew what the OH concentration was, you all remember the pH grid? So if you go back to the pH, to the homework page, oops, this one here, and we go to the coronavirus page, and we go back to a couple of days ago, where we were talking about the pH grid. You know that if you are on the pH grid with OH, then you could find POH and then pH. So what we're going to try and figure out how to do is find the OH, and then we'll be able to find the POH, and then we'll be able to find the pH. All right, so let's suppose that this concentration was 0.2 moles per liter. So it's 0.2 molar. And let's suppose if we know what we put in solution, we know that this is 0.2 and that's 0.2 because that's soluble, so it all goes away. It turns into these things. And you know, I told you a lot of times that in a saltwater solution, there's really no NaCl. There's Na pluses and Cl minus floating around. And the same thing holds true for this solution. So that means that this would be 0.2 initially. And this is an equilibrium, so it's going to go down by some amount. We don't really know how much. It's going to go down by X amount. So at equilibrium, you'd have 0.2 minus X. So 0.2 that you started with minus whatever reacts. We ignore water because you don't include liquids in equilibrium expressions. We know that there was none of these things when you started, but if X amount of that reacted, then you're going to have X amount of that produced. So we'll put plus X for both of those. And then at equilibrium, you'd have 0 plus X, and then 0 plus X, or just X. All right, so I just scratch out the 0 plus, and you just call it X. So now, if we write an equilibrium expression for this, we know that K, EQ, in this case, is going to be a KB. I'm going to put a B in there because you're making a base. So KB is equal to the concentration of the HC2H3O2 multiplied by the OH concentration divided by the acetate concentration, like that. So then you put in what you know from your expression. You'd have X was this right here, that's right there. The OH would be the hydroxide from here, and on the bottom we'd have 0.2 minus X. But we need to know a constant here in order to solve for X. So that constant I haven't taught you how to find yet. I'm about to do that. So if you look up the ionization constant for acetic acid, this acid here, you'll find that it is 1.74 times 10 to the negative fifth. Now that would be given to you in a problem, so I'm just going to give it to you here since we're in the middle of the video and I won't take time to go out and look that up. But if you look on a table, it'll tell you that that's the constant. All right, I want to show you a relationship now between Kb of an ion and Ka of its conjugate acid. So in this case, this was a base, and that's an acid. The water's an acid. So this would be the conjugate acid, and that is the conjugate base. So I'm going to show you the relationship between conjugate acid-base pairs. All right, so here we go. If I look at the ionization equation for acetic acid, it's HC2H3O2 plus water yields H3O plus OH minus. Excuse me, not OH minus, plus acetate ion. All right, and that's an equilibrium, like I said, equilibrium in the wrong spot there. So this plus this yields that plus that, and this is equilibrium. So if I wrote the expression for Ka here, I would have the hydronium ion, I'm going to write it underneath the Ka because it means the same thing, multiplied by the acetate ion, divided by the ionized acid or the acetic acid, like that. Okay, now I'm going to write Kb for the reaction of the ion with water. Did you notice, by the way, that I left water out of this? Because water is a liquid, you don't include liquids in the expression. All right, so on this one, this reaction of the ion up here, I'm going to have on top HC2H3O2 multiplied by the OH. And once again, I'm using these things here. And on the bottom, I'd have that acetate ion. And that would be a Kb. Now this is Ka for an acid and Kb for its conjugate. So any conjugate acid-base pair works this way. Now if I were to multiply these two things together, I have mathematically that would cancel and that would cancel, and I'd just be left with hydronium times hydroxide. And that, of course, is Ka times Kb. Well, the product of the hydronium and the hydroxide, you remember from our little pH grid, is 1 times 10 to the negative 14th, the ion constant of water. Or sometimes that's called Kw. All right, so Kw is equal to W is equal to hydronium times hydroxide. Or Ka times Kb equals Kw. Now remember, in this problem, we needed to know what Kb was for the ion. So I know the Ka for this acid, which I gave you, and you'd be given in a problem, is 1.74 times 10 to the negative fifth. So that means since Ka times Kb equals 1 times 10 to the negative 14th, that means that 1.74 times 10 to the negative fifth multiplied by Kb equals 1 times 10 to the negative 14th. And then you're ready to do the math, so pull a calculator out. So we would know we would have 1 times 10 to the negative 14th divided by 1.74 times 10 to the negative fifth. Oops, hit the wrong button there. Second EE negative 5. Okay, and that gives us 5.75 times 10 to the negative 10th. So up here, Kb that we need right there is 5.75 times 10 to the negative 10th. Okay, now we're ready to solve for x. So let's do that. 5.74 times 10 to the negative 10th. Multiply. Okay, before I go there, remember you can ignore the minus x because relative to the point 2, it's going to be extremely small. And the rule for that is if you ignore it, you can check your answer. If your answer is less than 5% of the original answer, of the original concentration, then it was okay to ignore the minus x. But for simplicity's sake, in this class, we're just going to say ignore the minus x. So we take their answer, 5.75 times 10 to the negative 10th, multiply by 0.2, and you get 1.15 times 10 to the negative 10th. So we'll write that down, 1.15 times 10 to the negative 10th. That equals x squared, so you take the square root, remember a shortcut for square root is just raised to the 0.5 power. And you end up with x being equal to 1.07 times 10 to the negative fifth. Now, how do you find P? Remember, that's OH concentration, and you find POH by taking the negative logarithm of that. So I'm going to go ahead and take the logarithm of that answer. So log of the answer, and that is 4.97. So the POH, and I just took the regular log, and that's a negative number, so I'm going to drop the negative and make it a positive number because a negative of a negative is a positive. So the POH equals 4.97. So you subtract that from 14, and you end up with pH equals 9.03. All right, and that would be the pH of our solution of potassium acetate if it was 0.2 molar. Now remember, we said that this is the salt of a strong base and a weak acid, so it should be a little bit basic. And our answer when we calculated it was 9.03. So we're right. Okay, now for those of you who are watching my calculator closely, a trick that I sometimes use is I just take log, and that was a negative number, and so if I write down the POH, I write down 4.97, that's positive. But in my calculator, I just left it as negative, so I can just hit plus 14 and I get the answer. So really, this answer is the same thing as 14 minus 4.97. Not sure anybody was watching that close, but just in case. All right, next thing I want to do is do a problem from a website. I'm going to do one that I left on your homework page, and one for which the answer was actually incorrect that was on the page, so we'll do that one. Okay, so we're going to we'll go all the way over to the coronavirus homework page. I left this up here for acid-base hydrolysis problems. And the problem I want to look at looks like this. So we'll bring this over. That a little smaller, come back to our webcam, get it a little smaller too. All right, there we go. So we're looking at first question. You have a pH of a 0.25 molar solution of sodium nitrate. So you have sodium nitrite, and it's going to come apart like that, or it's going to come apart like this. So Na plus NO2 minus. And these are both aqueous. So which ion is going to react? Well, it's the ion from the weak thing. It's going to react with water. So we're going to have this equation going on. NO2 is going to react with H2O. This is an ion from a weak acid, so it's a conjugate base of a weak acid. And the little rule is the stronger the acid, the weaker its conjugate base, and the weaker the acid, the stronger its conjugate base. So this is the conjugate base of weak acid. It's going to pull a hydrogen off of some of the waters, go into equilibrium and create HNO2, and then OHs will be left behind. These will all be aqueous, so I'll leave that part out. We know that the original concentration of the sodium nitrite was 0.25. Since that's a soluble salt, log goes away. That's 0.25, and that is 0.25. All right, now that means this is 0.25, and that would be our initial concentration. We don't have any of this, any of that, until this dissolves, and then that starts doing that. But before we start doing the calculations, we can assume we didn't have any of those. The change, we know this is going to go down by X amount, and that'll go up by X amount. And at equilibrium, we're going to have 0.25 minus X, and then both of these will just be X because 0 plus X is just X. All right, now we set up our expression. This is a KB problem. So you've got HNO2 multiplied by the hydroxide divided by the NO2 minus. The HNO2 and the OH are both X. The NO2 minus is 0.25 minus X. We need to find Kb, but we're given Ka. See right up here it gives us Ka, so we just learned that Ka times Kb equals Kw. So Ka was 4.5 times 10 to the negative fourth. Kb we're looking for, Kw is 1 times 10 to the negative 14th. Divide both sides by 4.5 times 10 to the negative 4th. So we'll clear everything out here. So 1 second EE negative 14th divided by 4.5 second EE negative 4th is 2.2 times 10 to the negative 11th. So Kb equals 2.22 times 10 to the negative 11th. So 2.22 times 10 to the negative 11th is what we would use there. So we went over here and used this Ka times Kb equation to find out what Kb was, and you plug it in over here. Now remember we said we could ignore the minus x. That makes the problem simpler because it lets you ignore the quadratic. So we take our 2.22 times 10 to the negative 11th, multiply by 0.25, and then divide, or take the square root of that. So to the 0.5 power, and we get 2.36 times 10 to the negative 6. So x equals 2.36 times 10 to the negative 6th. Okay, remember the pH grid. So here you go. We now have OH, because that's what x was. And we're going to take the negative log of that, get the POH, and subtract from 14, get the pH. And then we're done. All right, so here we go. So we're going to take the negative log of this, we said. So you can do a logarithm of that. Okay, so if I took the log of that, x was that, yeah, okay, so the POH, making sure I didn't make a mental mistake, it's getting late at night for a man of my age. So POH equals 5.6. So that means that the POH is 5.6, so the pH would be 14 minus that. And I get 8.37. Oops, that's the pH. The pH will be 8.37. Now, if you look at the problem, for some reason they have 1.97, which just isn't right. So maybe that's the pH of a 0.25 molar solution of HNO2. Today in class we did number 3, and that was right. So I think we can, this came from a community college in Mesa, Arizona. So I think you can assume the answers are pretty much right, except they just might have made a mistake on this first one. Yeah, those look in the right range. Yeah. Okay. So if I would say for tonight or this weekend, if you can get question 3 and question 4 right, you understand it well enough. Question 2 does not have a it's not a question about a salt solution. It's just the pH of a base, and they give you the ionization constant of the base. So it's actually a simpler problem. All right. So I'm going to stop this part of class, and I'll come back for one more part.